So this is a typical problem in thin film interference. You have an oil spill that occurs somewhere in the ocean in calm waters that just rules out waves and other disturbances. And you have an observer in a helicopter sent out to investigate the slick, report the slick as being black, meaning that no light is reflected. So find the minimum thickness of the oil slick. Also, a diver sent below the slick to investigate it will see what color. How will that diver report the slick? We're going to take lambda equals 550 nanometers for sunlight, which is the optimum wavelength for the human eye to detect sunlight. The oil slick's refractive index is 1.9 and the refractive index of water, as usual, is 4/3. Now, in solving a problem like this, it's very useful to draw a diagram to see what's happening. So let's draw a composite diagram consisting of the oil slick and then the water layer underneath it. And we're also going to consider normal incidence or near normal incidence. However, for clarity, we're going to draw it a little bit offset so we can actually see what's going on with the rays. So you have a ray that's coming in. Air is refractive index 1. I'll put the refractive indices within circles. The oil is 1.9 and water is 1.33. I don't have a calculator, so bear with me. I'm just going to give the answers as ratios. So you have this light coming in. It's going to reflect off the first surface. Well, the reflection here is going to be from low to high. So low to high phase change pi. That's how you remember it in poetry form. So there's going to be a phase change of pi. Now then it's going to go down. Due to Snell's law, there's going to be some refraction, which I'm not really caring to write. And then it's going to reflect off this surface. Now when it goes through, the transmission has zero phase change. But now it's going to reflect from high to low. Reflection of high to low, phase change 0. Or you can think of it as phase change O if you want to rhyme with low. So these are the two rules written in poetry form, and you've got to use that. So there's going to be no phase change upon this second reflection, and then when it goes through, again it's a transmitted ray, there'll be no phase change. So this one has got zero phase change. Now the observer from a helicopter is going to be watching this whole thing from the helicopter like that. So that's my idea of the human eye. So the net phase change between the two rays is going to be pi. Now the total path difference, however, is not just pi. The total phase difference also comes from the path difference here. So if the thickness of the oil is T, and that's really what we are asked to find, then the net path difference which I'll call capital delta, is going to be 2t, because I'm now going to think of the rays as being nearly normal. If it's nearly normal, it's going to be 2 times t, plus the path difference corresponding to the phase difference of pi. Now if you think about a wave and look at the complete wave, then a phase difference of 2 pi is what this entire wave is worth. It's 0 to 2 pi. And that corresponds, however, to a path difference of lambda. A full lambda is sitting within 2 pi radians. So within pi radians, the path difference is going to be lambda by 2. However, it's lambda by 2 in the film. In the film, the wavelength gets compressed. So it's going to be lambda over 2 times the refractive index of oil. So that's the total path difference. And now, because the observer is seeing that path difference as being destructive, since there is no light being observed, that's what the problem says. If you're seeing the slick as black, it means that then there's no light being reflected from it. So we need that delta is equal to m plus a half lambda. That's a condition for destructive interference. So now delta can be put in terms of this particular result here. So I'm going to get 2t plus lambda over 2n oil is equal to m plus a half lambda. And you can basically solve for thickness from here. By the way, the lambda here also is lambda divided by 2n oil. Lambda divided by n oil, not 2n oil. So this is an interesting situation because I have a lambda divided by 2n oil and a lambda divided by 2n oil there. So that's simply going to cancel out. So this gives me 2t equals m lambda over n oil, or the minimum thickness T is m lambda over 2n oil. Now we have been told there is a slick, so you cannot choose m equals 0. So the minimum thickness is m equals 1. And if you choose m equals 1, I'm going to get T equals lambda over 2n oil. And as I said, I don't have a calculator. I'll just indicate the numbers here. It's 550 nanometers divided by 2 times 1.9. And so that's the thickness in nanometers. Now the oil slick can be thicker than that, of course, because higher values of m can be used, but the thinnest minimum thickness is what's asked, and that's going to be given by that. So that's the first half of the problem is what the helicopter person is reporting that he or she is saying, and that's the analysis from the helicopter point of view. Now, from the viewpoint of the person, the diver, which I'll draw as an eye that's located here. So my diagrams are going to be a riot. So imagine that you have a diver there. So first of all, you can think of light rays as light comes from above. Okay, there's no light coming from below. So there's light always going to come from above. So this one light, the transmitted ray that makes through, will reach this person with no phase shift. That's for sure. And now we need another ray, otherwise we won't get an image. So what happens is this one that goes out like this reflects again. Now there is no law that says that won't happen. In fact, it's going to happen an infinite number of times. So it reflects again. The primary reflection is what causes the interference pattern. So it reflects again. Now, if you reflect from low to high, from high to low, phase change 0. So there'll be 0 phase change. Again, transmission is 0. So this is going to be both 0. So this person who is underwater, diver that's underwater, is going to have a path difference. So this is from the diver's point of view. That's for the helicopter. So I'll call it heli. So the net path difference here is going to be again 2t, but this time there's going to be no additional path difference coming from the phase changes. So that's just going to be 0. Now the question is, what is the helicopter the diver going to see? So we already know the thickness. The thickness is going to be given by lambda over 2n oil. So this is going to be equal to lambda over n oil. Now what we have to decide is, what is this? Is this descriptive more of m lambda over n oil, which is the condition for constructive interference, or is it more descriptive of m plus half lambda over n oil? Which of these two possibilities is entertained by 2 times the thickness, the path difference? Clearly we see that only m equals 1 produces, in case of the constructive interference, only m equals 1 produces this result. So for the person underwater, they're going to report the oil slick as having some color. In fact, for the person underwater, the oil slick will have the color given by lambda over n oil. So if you think about it, it's going to be 550 nanometers divided by 1.9, which really doesn't look to me like visible light, but it's going to be that wavelength, whatever that wavelength is. So it's going to be compressed. Now, a compressed wave is a wave that's more to the ultraviolet range. A stretched out wave is more to the infrared range. So this is going to be more in the violet range. Okay. So that person is going to describe the slick as being a violet slick rather than a black slick.